Hello students, welcome back to another class on a series of lectures on classical mechanics, and today we are going to have lecture number 9. In the previous class we have seen an introduction to the phase space plotting and the important terminology associated with it. So the purpose of introducing the phase space is that the concept of the mathematical space should be familiar. That is one of the important reasons, followed by some terminology such as orbit, trajectory or flow. Flow is more important that we will be using. It is known as the flow of a dynamical system. The equivalent statement to the flow is temporal evolution of dynamical system. So the traditional way of speaking about the mechanics is the temporal evolution. Temporal evolution means the evolution with respect to time. And in the phase space dynamics, when we are going to discuss, it is known as the flow of dynamical system. So because of the word flow, you should not feel that there is something fluid there. Okay, but the terminology is used because of the arrow that is going to draw. We are going to put some arrow in the phase space representing the increasing direction of time. That is the reason why we use the word flow. So the primary reason for introducing the concept of the phase space is the concept of manifold, the concept of topology in higher dimensional mathematical space, and then we need to use frequently the flow and the phase space trajectories. So these are some of the basic requirements that we need, and that we have completed to a fairly good extent. There are further studies can be done with respect to the classification of fixed point, and we can take some more examples and study or even solve a particular dynamical system, but that is not very important for this course. It can be done, of course. Okay, it can be done as additional exercise, but let us focus our attention to the Hamilton's principle, because that is the main topic of the first unit for you. Okay. Hamilton's principle, I don't want to write the statement straight away and then it looks like, repeating the same statement or the principle which is copied from the book. It will appear like that. So that is not the plan for us. Let us understand what is this principle is all about. So the principle is something that exists in the nature, not necessarily in the physics. Okay, it exists everywhere in the surrounding. So if you look back in the history, you can see many things related to the Hamilton's principle. In fact, Hamilton's principle itself came as a consequence of refining the previous discoveries. So that is why if you can look back in the time scale, that means historically, sometime in 1650s, we can see what is known as the Fermat's principle. And very close to this time, for example, 1680s or something like that, 1686, you can see the Newton's laws. Okay, so in fact, the Fermat's principle in optics is closely connected to the Hamilton's principle that we are going to see. And you already know that the Hamilton principle itself was used by the Lagrange in order to derive the Lagrange equation of motion. And the purpose of deriving the Lagrange equation of motion is to understand the existence of, or to understand the theoretical foundation behind the Newton's laws. So that's why I'm writing Newton's laws here. So everything is connected in a way. That's what I'm trying to say. And then if you are again looking back in time after 1600s, sometime in 1750s or so, roughly around the 1750s, Lagrange himself has put forward certain principle, and that is the Lagrange's principle. Let me write down that. So in 1750, you can see the Lagrange's least action principle. So all are related. Okay, even Fermat's principle is also some kind of least action. So I will explain that. And then once this is put forward by the Lagrange, this has been generalized to a more general situation, and that is what is put forward by the Hamilton. So that's what we are now coming. So this is the Hamilton's principle now. So this is the historical evolution of the basic principles that have been developed over the time. So actually Lagrange himself is there in the discussion, and his principle is also a least action principle. Hamilton's principle is also a similar principle, but instead of saying least, he tried to add either least or it can be maximum. Least means minimum. And Fermat's principle, you know that it is also a minimum. So what is that minimum and what can be maximum here? That's what we are going to see. And if you are going to see all this historical evolution, the overall idea or the overall concept behind these people's mind is always some kind of minimizing. Least means minimizing. Certain things are getting minimized. And Hamilton is a person who said not necessarily minimization. Why to minimize all the time? You can also maximize. So that was the thought that Hamilton brought it. And as you can see, all of them, by the way, all of them are mathematicians, including Newton. Newton by himself, he is considered as a mathematician because Newton is the person who put forward the concept of derivatives. The very beginning, the concept of differentiation itself was brought by Newton. And later it was developed formally by Leibniz and other people. Okay. So, and you can always see the Newton's Cotes integration formula, Newton's formula for backward and forward differences. Many formulas are there in mathematics also. So Newton himself is a mathematician. Lagrange is another mathematician. Hamilton is also mathematician. So all these people were trying to have something in common, namely something is going on in order to minimize and maximize. That was the overall idea. And in fact, this idea came to their mind because you can always observe something in individual without having any kind of technical aspect. Now I mean to say in a daily life, if you are going to see something like everyday life, for example, forget about the subject, no physics, nothing. Okay, some a general life is there, and then if a person is planning to have some he is applying for a different job, for example, and then he is going to an interview, different interviews. He got selected in 4 different companies, got the appointment orders. And then the question, then your friend will ask, what is the action that you are going to take? Because you got the 4 you got the 4 appointment orders. So in which company are you going to join? That is the question. And in addition, he asked the question, what is the action that you are going to take? So here the word action is the point that you have to remember, because this is the word that we have been using in the daily life, and the same word action is what we are going to use in physics also. And you can now understand what is action. Action means that an individual is going to perform something, that is the action. And what is in this example, what is the action is that which company are you going to select and where are you going to join? Okay, that is the question. And the answer is that what answer will you give is the company that is going to give you higher salary, whichever company is going to give you the highest possible salary with other facilities, whatever possible. Okay, that is the maximum gain or maximum income. So that is the thing that will enter into your mind. So your mind will work based on maximization of the income. That is the thing that is going on in your mind, and based on that you are going to select a particular company and join. Selecting a company and joining is the action. And why did you take that action? If you ask the question, then the reason comes out as maximization. So the reason is not trivial. It is not visible to you. What is visible is only action. Okay, but what is not visible is minimization or maximization. In our example, it is the maximization of the salary. So therefore, I will now write down here that the action is connected. I am now writing here. Action is connected with either it can be maximization also. You can. It is not necessary that always maximization. It is not necessary that always minimization. It can be either this one or that one. It cannot be in between. That is the interesting point that you have to note down. No one will choose randomly. Okay, I will close my eyes and choose one of the letters, one of the appointment orders and go and join. Like that, no one will do. Okay, if you do that, then there is no maximization, there is no minimization. You randomly pick something. That kind of action no one will do. So therefore, your action is based on either the minimization or the maximization. So in this example, maximization, that's quite clear. That's fine. Now what happened? You are working in that company, and when the first day of the month comes, you get the salary. Then you ask the question, okay, you got the salary, and now you are going to spend the money, okay, for your family. What is the principle are you going to use? You want to maximize your the money that you are going to spend, or minimize? So naturally, everyone will tell that I want to minimize the expenditure. So when you are spending the money, you want to minimize, but when you want to get the salary, you want to maximize, which means that an individual's action, that is called action, is based on either the minimization or the maximization principle. That principle is running behind the mind. Your mind is working based on that, and therefore that's not visible. But what is visible is the person, what he is doing, that is only visible. Okay, so therefore action is visible, but the reason behind the action is invisible. And the reason behind the action is what is the mathematics. So that's why I already told you that the mathematical space is invisible. You can't see it. Okay, but however, the equations and the feeling of the equation, that should bring you the concept of the mathematical space and what is going on in that space. Okay, so let me again write down that the action, the same action is once again connected to the minimization also. In any event, you want to maximize something, you want to minimize something. So what are you going to maximize and what are you going to minimize? That will change from one problem to the other problem. That is known as objective function. So let me write down that objective function. So objective function is a proper mathematical word or mathematical term that is used in the optimization theory. So the whole thing, whether it is maximization or minimization, whatever you do, the mathematics behind minimization and maximization is known as optimization. So let me write down that also. So optimization theory is the mathematics behind the minimization and maximization. And in that theory, the first question that we ask is, what is the objective function? Objective function means what are you going to maximize or what are you going to minimize? That is written down as a function. Okay, in a plain language, I said that you are going to do salary and expenditure, but in mathematics, you have to write down what is the function for that. That function is known as objective function. And the optimization theory is the one that is the general term in mathematics. And in particular, within mathematics, what is the topic that we are going to use in order to do the optimization is the calculus. And therefore, the particular subject area that does this work is known as the calculus of variation. So these are the terminologies that I am now introducing. Optimization theory is a very generic and very broad term, not necessarily limited to any particular subject. Okay, it can range from anywhere from science subjects, and it can go to finance and any other general topic. Okay, you can always optimize certain thing. That is an optimization theory. And in particular, what kind of mathematics is being used is the calculus of variations. In particular, calculus is used. Variation means you are allowing to change. What are you going to allow it to change means, if you are going to fix, suppose if you are going to consider salary, then you allow the salary to vary from some number to some number. When you have the four companies appointment order, you have what is the salary given by one company, second company, third and fourth companies. When you write down that, you have a minimum value and then you have a maximum value for the salary. That is the variation. Okay, from what value of the salary to what value of the salary, minimum to maximum. That difference is what is known as variation. That means for a given educational qualification that you have a variation of salary from here to here. You are now eligible to take a particular job. That is called variation. Variation means allowing something to vary from one value to another value. That's the variation. So from topic to topic, you can always tell what is the quantity that you are going to vary and how much you are going to vary. And coming to that variation, when we are talking about how do you represent the variation is by the symbol delta. So delta is the symbol used for variation. You can vary anything. You suppose if you are going to vary length, for example, then you write delta L. I write delta L. L is the length I want to vary. If you are going to have a rubber band with you, I can pull the rubber band and then increase its length from some value to another value. Okay, so you have the freedom to pull the rubber band and then take whatever length you like. So there is a variation in length, and that is delta L. So delta is the symbol, general symbol, mathematical symbol used for representing variation. So you should not confuse this with the traditional derivative symbol like this, such as dl or something like dou L. Okay, so these symbols, when compared to these symbols, this means that you are going to allow a variation to take any value starting from some L minimum to L maximum. That is what it means to say. That's all about it. Okay, so these are the standard terminologies, and now we will come back to our original discussion and see what is getting minimized and what is getting maximized. Okay, in the case of this, let us come to this Fermat principle, because you must be already familiar with this. You must have already studied optics. So Fermat principle is once again the principle of least time. So here, what is the least? That's what I am trying to say. Minimizing of something instead of length, instead of distance, instead of whatever quantity that we are planning to minimize. In the case of the optics, Fermat principle tells that it is the minimization of time. So you should remember that we are going to talk about delta t. So if you are going to consider the light ray that is going to travel from a point A to another point B, this is the point B, and you are asking the question, what is the path the light will take? That is the question. Apparently the answer is a straight line, but not always true. Straight line is correct, but will it be a single straight line or multiple straight line is a question. Okay, if you don't have anything in between A and B, which means that you are having a single medium of index, that means material. Medium means, so let us say air. Same air is there between A and B, then you can always join a straight line, single straight line. But suppose if you have a glass bar, for example, if you have a glass bar like this, okay, you can draw something like this schematically. This is made up of glass, and once it is glass, you know that it has certain refractive index and other things. So now what happens is, straight line you can't join. Okay, you will have to draw something like this, some schematic diagram I am drawing. I am not drawing accurately. I am not drawing it accurately, keeping the angle of refraction, etc. This is a rough concept. I am saying that you will not have a single straight line, but you will be having double. One straight line is here and another straight line is here, which means that refraction phenomenon is taking place, and therefore two straight lines are required. Now the Fermat principle is going to give you explanation for this. What is the explanation is, suppose if the light is going to travel along a single straight line, let me draw that in the orange color. Let me draw a line in an orange color from here to here, from A to B. That is a single straight line from A to B. You are asking the question why the light did not travel like that, even though there is a glass bar or some kind of medium is there in between. The answer is, if the light is going to travel along the orange color line, which is a straight line, then it will take more time to reach the point B when compared to the same light traveling from A to this particular point. Let us say that this is C. Okay, I can call this as C. So therefore A, C, B, that is the path. Then that will give ACB path will give you minimum time, whereas the direct path AB will give you a little higher time. Light want to reach the destination as quickly as possible. That is the objective of the light. So light is having in its mind that I want to reach the destination as fast as possible, not minimum distance. Okay, light is not thinking that I should travel along a minimum distance. It want to travel along a path in such a way that the time has to be minimum. It has to travel as fast as possible. So that was put forward by the Fermat, and this principle is the one that is successfully able to explain the refraction phenomena. Otherwise, if you simply say that the light is going to travel by the shortest distance, okay, shortest distance, then it doesn't work. Shortest distance concept will not work to explain the refraction phenomena. Therefore, the principle of the Fermat is that of the least time or minimization of time. So the concept of minimization and maximization you are able to feel now. It is there in everyday life. Everywhere not necessarily in physics. And even if you ask, even the everyday life, if you ask, for example, if you are reaching a bus stand, for example, after traveling and get down from the bus and take an auto, the auto driver will take you in some kind of road and then reach your house. Okay, whereas you will not travel like that. You will be always traveling in some main road. So if you ask the auto driver, why are you traveling in such kind of road, then ultimately he will say that I want to minimize the petrol. Okay, I want to minimize the petrol, and therefore I am traveling in these kinds of road. So that's what that means. Based on his thinking and based on that is what is the action. Now you understand what is the word action. You want to minimize something. So based on the minimization, he is taking an action, and that action is what is visible. That he is taking a different path and then driving his vehicle. That's an idea. So it takes place everywhere. And now let us come to the concept of the Lagrange and Hamiltonian. In fact, Lagrange and Hamiltonians, the concept is the same. Only difference is Lagrange says that only minimization should be there. But Hamilton says, why only minimization? Let us also have maximization. It is possible. He says that it is not just saying maximization is also allowed, but he also gave examples that maximization is possible. So let me just explain where is the maximization is also possible. So do you remember, or are you able to recall anything that you already learned that has a maximization taking place? So the answer is yes. You studied thermodynamics, right? So in the thermodynamics, at equilibrium, suppose if you are going to have a closed thermodynamic system. Okay, closed thermodynamic system means you have internal energy, and then you don't allow the energy to go outside. Nothing should come inside. Okay, the material inside should not escape outside. None of the gas molecules should enter inside. Okay, that's called a closed system. So when you have a closed thermodynamic system, and if you allow that system to come to equilibrium, thermal equilibrium, then entropy is maximized. So that is the concept that should be familiar to you because you studied thermodynamics in your BSc. So if you are going to write S is the entropy, so this is getting maximized at equilibrium. At thermodynamic equilibrium is very, very important. If you don't tell whether it is equilibrium or not, then we also cannot tell whether entropy is minimum or maximum. It is neither. It will be neither. It will be fluctuating, and then it will be in the process of reaching somewhere. Okay. So only at equilibrium this is the statement. If equilibrium did not attain, then we cannot tell anything about the entropy. So therefore, entire thermodynamics that you studied, remember that it is equilibrium thermodynamics. That's very important. Non-equilibrium, no, we can't. So only you allow the system to equilibrate. Until that you have to wait. Once the system has come to an equilibrium, only then you measure. Okay, whether you are measuring energy or entropy, whatever it is, you do it at the equilibrium. So all the studies that you do under the name of thermodynamics is at equilibrium. Therefore, it is known as equilibrium thermodynamics. Okay, so this is clear that maximization. So this is an example where maximization is also possible in physics, and therefore we should not always say minimization. So either maximization or minimization. So therefore a new name therefore comes here. So therefore let me write down here. It is either maximization or minimize. Now these two things, instead of telling every time either or, it will be boring. So if you can discover another better English word, it is good. So that word is the extremization. So I'll write down that this is known as the extremization. So if I tell that the physical system is extremizing, what is the meaning? That means it is either maximizing or minimizing depending upon a particular system. Same system will not do both minimizing and maximizing. Anyway, that's not possible. Okay, one system will do minimization, another system will do maximization, any one at a time. But the general terminology would be extremization. Therefore, now it is clear that if you are going to consider the Lagrange's principle, then it is known as least action principle. As you can see, least tells means minimum. Least means only minimum. Similarly, Fermat principle is also minimization of time. Therefore, that is also known as minimization. we can say least action. So the word least action can be used only when the system is minimizing. No maximization should be there. Under such conditions, you can use the word least action. Least is minimization. Action, just now I explained. Based on that kind of minimization, whatever is evolving out or whatever you are able to observe, that is the action. So that is why it is called least action principle. But Hamilton principle is not a least action because it could be either minimum or maximum, and therefore Hamilton's principle is the Hamilton's extremo principle or extremization principle. That is why it is not explicitly written here. Simply we say Hamilton's principle. We don't say Hamilton's least action principle, okay, but rather we will say Hamilton's extremization principle. Like that you have to say, so that it is applicable for either way it is applicable. So thermodynamics, we have seen an example where the maximization of the entropy is possible. Coming to the mechanics, in fact, your first year BSc mechanics you already studied, and there you know very well that something is minimizing. This is very simple. So I will show you a diagram here. Let me draw one diagram. So if you are going to have a shape like this, so this is a bowl. Let us say that this is some kind of a bowl. I'm just drawing the cross section of the bowl, so it looks like that, but in 3 dimension you must be able to see the bowl. This is cross section. Cross section means you cut it vertically, and then what you see from the front, it's a front view. That's what I have drawn. It looks like a parabolic one. And suppose if you drop a ball here, you take a ball and then keep it here, you hold the ball here and then release your hand. Then what happens? This ball will come down, then it will go up, then again it will come down, then it will go up, but it will come only up to this, again it will come down, and again it will come up, and finally what happens is it will come here. Okay, so in between, why the amplitude reduces, all these things, you know, friction or air resistance or whatever it is. So those dissipations will reduce the amplitude, and ultimately, finally what happens is that this is the final position. That's what we are interested in. So this is the final position of the ball, and this final position is what we say equilibrium. Let me again tell you the word equilibrium. The equilibrium is very important word, both in the case of thermodynamics as well as in mechanics also. In mechanics also you always study equilibrium, static equilibrium, dynamic equilibrium. So all the calculations are done under equilibrium conditions. Okay, when you want to study dynamics itself without equilibrium, then it will be only instantaneous values. That is, instantaneous values will be there without allowing it to equilibrate. But suppose if you allow it to equilibrate, then this particular ball will come and reach the bottommost position, and then it will stop. Afterwards, no more oscillation. That will be the stable position. And then you ask the question, why nature has chosen that position? Why it is coming here? So why it cannot stay here? For example, this dotted portion, I said this ball can stay there actually. Why it has come down? So if you ask the question, the answer comes like this. Every mechanical system at equilibrium is most stable when the potential energy is the minimum. That's the answer. So every mechanical system will be in its stable condition or stable position when its potential energy is minimum. It means the system's potential energy. So in this case, this potential energy, all the potential energy is corresponding to only the ball. The ball is very stationary, so we are not going to consider the energy of that. So we are going to ask the question, for which position of the ball the potential energy is minimum, and we say that this is the position. This is the position for which potential energy is going to be minimum. So that means nature is working based on this particular point in its mind. Whose mind? Nature's mind. In the nature's mind, it is having the principle. The principle is that the potential energy should be minimized. So therefore, once again, now you see that minimization principle is going on. So minimizing and maximizing is something that goes on everywhere in the universe. It goes one way or the other, it goes. That's the point. So ultimately, we are now, something is clear about the Hamilton's principle now. Hamilton's principle says that every dynamical system will be doing its action based on certain minimization or maximization, and that's all about it. And we are going to write it in a formal way. That means instead of saying in a simple English language, it is better, or it would be, being a mathematician, Hamilton being a mathematician, he want to write down this in a proper mathematical language. So that's what we are going to do. So let me write down now. Yes, so here I have written the Hamilton's principle. So first I will read it and then we will explain what is the meaning of the statement. So among the infinitely many paths available to the dynamical system, the actual path taken by the system is the one for which the quantity, namely this integral, is an extremum. That's the statement. So almost all the words are familiar to you now. The only thing is that the quantity is something that has an integral, and this is the integral if you are going to give the name. For let me say that this entire thing, let me put this round here. We will give the name for this and let us say that this is action. Then it will be clear to you. So the action we give, because it is that is the traditionally we understand the action and the reason. Okay, why you are doing, then based on that the action is the consequence. So for that reason, action is a typical terminology that is used. Now in this particular case, this will have the physical dimensions of, you can see what is the physical dimension. Lagrangian will have the dimensions of energy. So let me write down that. So energy multiplied by because there is a dt there, it must have a time. So energy multiplied by time. For the case of the dynamical problems or dynamical systems problem, we have this kind of definition for the action. So it is not that every time it is integral of L. Okay, for the classical mechanics where you are planning to discuss the reason behind the Newton's law, this is the expression for action. But if you are going to discuss a different problem, the appropriate action has to be written down. Okay, so that concept is there. But Hamilton principle itself was originally devised to understand the Newton's laws, and therefore the expression is written like this, where the action is actually the integral of the Lagrangian. And why integration is done, and then in fact the Lagrangian, why it should be q dot t, that I will explain now. But before that, it is most general that whether it is this topic or any other different topic on the minimization maximization principle, action is something that is going to have the dimensions either energy multiplied by time, or there is another option is there where you can have a momentum multiplied by length. So these are the most generally encountered physical problems. So you take a physical problem and then try to discover what could be the action. Then it ultimately turns out that the action would have the physical dimensions of energy multiplied by time. Most probably you should be able to recall the Planck's constant. No? That is the one that has the units of joules multiplied by second. Okay, or it could have, alternatively, some other systems could have momentum multiplied by length. So these are the possibilities. But for now, for mechanics anyway, the first option is the one, energy times the time. That is the reason. The second thing is, let us come back and explain what is the meaning of this. Among the infinitely, I am reading the statement now, among the infinitely many paths available. So where is the infinite paths available? Where is it available? That is the first question. Second thing is, so out of that many number of paths, the actual path means the one the dynamical system is ultimately chosen. Okay, you observe the one which you are observing, right? That is the actual path. If you are oscillating a pendulum, and then if you ask the question why the pendulum is oscillating like that, that is the actual path. See, this is something that you'll have to think. So why the pendulum should oscillate like that? It can oscillate in a very different style. Like that you have to ask. Then you come to the answer that, okay, there are infinitely many paths are there, or there are infinitely many ways in which the pendulum can oscillate. But even then, the nature only chooses only one among them, and that is what you are seeing. That seeing is the observation. That is the observation that you do, and then you are noting down the readings by measurements. So why should the dynamical system behave like that? Only one path, why is it choosing? That is the one path. So before that, let us see where are the infinitely many possible paths that we will see. and then we will discuss more about this integration of L of q comma q dot comma t. So that's what we are going to do. So therefore, before I will go to the next board, or I'll put a page down here. So hopefully you have written down this so that it will be easy for you to follow. Now, to understand where is the infinitely many paths, let us come back to the yesterday's classwork where we have drawn the phase space diagram corresponding to a simple pendulum. So that I will draw. The phase portrait will be the circle. Okay, that is the orbit. The orbit is the circle. Okay, so that is the circle I have drawn, and let us draw some arrow here. For example, in the last class we have the arrow like this. We started here. I think that is how we started. And if this is the starting point where I am putting a big dot here, and then if we are going to increase the time, so as time increases, this is the path that is taken by. And the axis should be, of course, written down, namely the theta along the x-axis and theta dot being the y-axis. So that is the phase plot. Now the question is, what is meant by path? The path is this one. The one that is drawn as a circle, right? That is the path. So then the second question is that where is the infinitely many paths? That's the question that you are asking. And for that, what you do is, let me draw another curve and then show it. So this is the starting point, right? So let me start from here. Now I am going through this path, and then I am coming like this. Now I am coming back to the original place. So this blue color line, I will call this as a trajectory. So rather than saying line, we can use the word trajectory. And then I can put an arrow like this. Now why the pendulum is not oscillating like this? That is the question. So it can actually take a different path along the theta versus theta dot double dot. Sorry, not double dot. In the y-axis I have drawn a mistake, right? The y-axis is not double dot. It is a single dot. So theta single dot. Okay. So now you will be able to understand how many such paths can you draw. That means circle is already taken by the simple pendulum. Simple pendulum says that I will oscillate only according to the phase space diagram, which is a circle. That's what pendulum says. You are saying that why did you choose that path? Why can't you choose some other path as I have shown here? So like this, can you draw still many possible paths? The answer is yes, right? You can draw a large number of paths. For example, you can draw like this. Say now I am drawing in pink color. Okay, the pendulum can take the oscillation in such a way that it can follow the pink color line. So you are asking the question, why pendulum is not following this? Why only circle? So the question is now clear that how many paths are available in the phase space? The answer is infinitely many. Okay, one is the arbitrary shape that I have drawn in blue color, and the other pink color line I have drawn something like square. That is another different path. Like this, I have infinitely many ways of showing different kind of trajectories. So that is called infinitely many paths. So in the phase portrait, it is always possible to draw infinitely many different paths and trajectories. It's always possible. Now out of that infinite possibilities, nature chooses only one. So now what is clear is, even though infinitely many possibilities are there in the phase space, nature chooses only a particular one. That is the statement. That is what is the statement that we have written. That is the Hamilton's principle. Now that statement is clear. So even though many options and possibilities are available, only one is chosen by the nature. And that decision, only one it is choosing, right? How did you choose that? That's the question comes. The answer is given by a particular action, and that action is what is written down as the Lagrangian. So the L is the Lagrangian. So Lagrangian is a function of fine that you, I think 2-3 classes before we have already seen that the position of the particle and then the q dot, the velocity of the particle. These two things are very important because they are the two quantities that enter into the phase space. You have the x-axis is q. This theta is what is q. Theta dot is the q dot. So this is the q dot. So therefore q comma q dot is the most common way to write down for this particular phase diagram or phase space diagram. If you are going to a totally different problem like thermodynamics, for example, then the corresponding variables are totally different. There you will not have q dot. Okay. There you will be having pressure, volume, temperature, etc. So that part should be clear. So for the time being, since we are discussing on the dynamical system related to the mechanics, we can write down q comma q dot. And it is going to be a mathematical function of these three variables, possibly time. Sometimes time may enter. Now you have such a quantity, but however, why do you want to integrate? But there is the point is important, that there is an integral is there, and this is a definite integral. Okay, that means you have a t1 to t2. What is this t1 to t2 is? This is the starting point. There is a starting point and there could be an ending point. Ending point should be there. Ending point means at least it is the time up to which you do the experiment. You may be doing the experiment for 20 oscillations. Then the last oscillation that you counted, after writing down that particular reading, you forget about the pendulum, you come out of the lab. You don't worry what is happening to that. So that particular last observation could be time t2. So t1 and t2 is that a particular point in the phase space diagram, not necessarily starting point. Starting point itself can be taken as t1, but not compulsory. It need not be. For example, if I am going to do an experiment, measuring 10 oscillation, 20 oscillation, 30 oscillation, 40 oscillation, then it is not necessary that the starting itself should be t1. You can always consider that t1 could be the 20th oscillation and t2 could be 30th oscillation. You can choose any two time. It is just a statement saying that choose any two time in between your experiment. You can't go before your experiment, nothing will be there. You have to start the experiment, right? So after starting the experiment, you choose any time as t1. And before closing your experiment, you choose another point t2. That's all it means. And that is your t1 and t2. And then the integration over the time. Now since it is written here t1 and t2, it is t. That means time. So therefore naturally dt comes. So integration should be with respect to what you are talking about. And we say that it is with respect to the time, because the phase space diagram is drawn for time, and that is why the arrow comes, this arrow. So therefore formally if you are going to choose any two times, I can now show it in the yellow color line, for example. Let me show here. This is the yellow color dot that you have, and that could be another dot. So this yellow color dot can be a t2, that could be a t1. That is the meaning. You choose any two time. And I have drawn it, actually I have drawn it on the white color circle. But how do you know that white color circle will come? Circle will come. We do not know, right? And therefore what you do is arbitrarily in a curve which is not at all known to you, on that you can show. So it doesn't matter whether you show it on the circle or corresponding time can be shown here. In the same t1 could be this, t2 could be this, equivalent. I am telling that equivalent t2 can be here. In the case of the blue color line, this could be t2 and that could be t1. This could be t1. So conceptually, when you are writing the equation, what is t1 and t2 is what you are showing. You need not show it on the actual path, because actual path itself we don't know. So we can arbitrarily draw some curve and then fix the 2 points t1 and t2 and then write down this particular quantity, and then we will call this quantity by the name action. And since it is an integral, we say it is action integral. That's nothing to, if the action itself doesn't have integral, then no need to call by the name action integral. In this problem, action happens to be an integral. That's why you say action integral. Otherwise, action need not be integral all the times. So these are the meanings that you have for this, and therefore now you can easily understand among the infinitely many paths available, the actual path taken by the dynamical system is the one for which the action integral is an extremum. So action integral is an extremum is there. So that is the condition. So now you have to now give a mathematical way of saying how it can be an extremum. So this is action is clear. How do you say that the action integral is an extremum? That you can write, that concept is quite simple. because you already studied maxima minima in mathematics, and therefore we say that the variation, now I am writing the delta. Delta is variation of the action if this is equal to 0. So you put the condition if, now I am writing the condition, if the variation means, well, in the simple mathematics or the first calculus course that you learn, you always put the condition, right? dy by dx equal to 0. If dy by dx equal to 0, then that is the condition for minima or maxima. Okay, that's what it is. So same thing that we are writing, if the delta is the variation, that variation should be on the action, that means that the delta of that is equal to 0. This is equal to 0. Then we say that it is a condition for maxima. So then it represents condition for extrema. So that is what it is, which means that in our problem, how do you write is that delta of put the action integral now. This is t1 to t2 of the Lagrangian, and Lagrangian is a function of q dot and t, and then multiplied by dt should be equal to 0. So this is what is going to be the important rule that we are going to use. So there is a if here, you have to put this. So that means if the delta of the action is equal to 0, then if that condition is satisfied, then the curve or the trajectory for which this condition is satisfied is the one taken by the nature or the dynamical system. Now coming back to this diagram, you can now immediately tell which one of the curve. Now we have three options: blue color curve, pink color curve, and the white color circle. For the three of this diagram, which one of them will satisfy this if condition? So this if condition is there, right? So let me therefore take this in white color, and then I'll show that this white color circle, I put a arrow here and then say tick here. I am putting tick, which means that we ask every time this question, whether this delta of the integral is 0 for blue color. Then you say no, it did not happen. Okay, mathematically you can always calculate by an equation, evaluate the delta of the integral along the blue color curve or the blue color trajectory, and you will discover that it won't be 0. Then you ask the question, what happens to the pink color curve? Whether this if condition satisfied, you ask the question. So for the pink color one, once again I'll put it, this one, for the pink color curve, this delta condition will not be satisfied. So I am putting an into mark. Okay, that means the variation condition, delta of the action integral, that will not be satisfied. So again into mark. Like that, you have to repeat it for infinitely many trajectories. You first draw infinitely many trajectories, and for each trajectory you ask the question whether the delta of the action integral is 0, and if it is not 0, you reject. If it is not 0, you reject. If you do like that, you will ultimately discover one curve or one trajectory for which the delta of the action integral is 0. And that is the path taken by the dynamical system. And that's all. That is a conclusion, which means that nature works all these calculations behind the scene, and then only when this delta of the action integral is 0, it chooses that, and according to that the system oscillates, whether the system is oscillating or moving or whatever it is doing. Okay, that is a dynamical system. Whatever dynamics it is doing, that dynamics is because of the delta of the integral equal to 0. That condition is satisfied. So this is what is the Hamilton's principle. And if this happens, okay, and if this happens, then the corresponding equations of motions are the Newton's laws of equation. The Newton's second law that you write F equal to ma, right? That is a consequence of getting the circle. That means you first got the circle here, and corresponding to that circle you have F equal to ma. If you are going to take the blue color trajectory or the pink color trajectory here, F equal to ma will not be valid. It won't be valid. So that means F equal to ma itself is by nature. I mean, nature means direct natural measurement. You directly do an experiment and measure it, and from the observed data, you just find out what kind of equation is suitable for that data. And then ultimately F equal to ma is what is the discovery. That was the discovery. And in order to do that discovery, Newton himself has discovered the concept of the derivative. Otherwise, velocity and acceleration requires two time derivatives, right? So at the time of Newton, there is no concept of differentiation. So Newton himself discovered the concept of the derivative. Then he introduced the velocity and acceleration, and after that he says that F equal to ma could be the suitable equation corresponding to the observed data based on experiments. So that was the long time back, 1600 and something, like 1650 or so. So this particular explanation by the Hamilton in the mathematical theory gives you the reason now. So this gives you a mathematical reason that the particular path that is chosen by the dynamical system is only one special path out of infinite choices. So, and the whole thing works based on the minimization or maximization principle, which is generally coming under the category of calculus of variation. So hopefully this kind of explanation should give you fairly good meaning to the Hamilton's principle, because Hamilton principle in itself is going to describe on the phase space. So basically you are going to draw it in phase space and understand the integration. So the integration is done in the phase space variable. This is the first point that you should know. Phase space variable means q and q dot. These are phase space variables. And then if this is a mathematical function that you will write down L of this, then variation on that means delta of that, which is essentially nothing but you are going to perform the usual differentiation. Let me tell you what is the meaning of this delta of this. Suppose if f is a function of x comma y, then how will you find out df? This you already know. It's a function of two variables. Then we can always write that df dou f by dou x dx plus dou f by dou y dy. This quantity is what we say variation. Okay, f can be varied like this. So the meaning of this particular df is that you can either achieve f plus df or you can go for f minus df. That is, f is allowed to vary this side or that side a little bit. Okay, so the variation is what is given by this quantity. So that can be calculated. If you have a function of two variables, then this is how you do. Function of three variables, you add one more term. Function of four variables, you add another term. But the whole idea is that you can always do this kind of calculation on this. That is what is the meaning of this delta L. That calculation we will do in the next class. But however, before closing this particular topic, I will also would like to tell you that in the case of thermodynamics, if you are going to have thermodynamics, you have the pressure, volume and the temperature. These are the most frequently used variables and which you can control. Some of the variables can be controlled and some other things you are going to measure. Suppose if you are going to fix volume and the temperature, you fix it. Fix it means as a constant. Okay, you keep the temperature constant. Okay, and then you keep the volume of the thermodynamic system also to be a constant. Something like closed chamber, okay, where the chamber is not expandable. Metallic chamber you take, that's a fixed volume and maintain a uniform temperature. That's an example of a thermodynamic system where you are going to fix these two variables are constant. And then inside this chamber there is something is going on. Okay, it may be some gas is getting heated up or whatever it is, and then maintaining at constant temperature. Now the question that we are asking is, at thermodynamic equilibrium, what energy is, how do you fix the energy? So the energy of the system, if you are going to consider this particular system, the conclusion is that the Helmholtz free energy will be a minimum. So this example I am trying to give because thermodynamics is something that you must have studied typically in the second year of your BSc. So you will be having this idea. Now it's a time to refresh your memory on minimization and maximization. Okay, I have given the entropy maximization in thermodynamics once again. So I thought I will give another example again in thermodynamics so that you can feel the maxima minima principle everywhere. So, but remember that when the volume and temperature are fixed as constants in your experiment, then at thermodynamic equilibrium, your thermodynamic system will be controlled by the Helmholtz free energy. Okay, it will equilibrate when it becomes a minimum. If the Helmholtz free energy is not a minimum, that means the system is not in thermal equilibrium. You'll have to wait for more time. That's the meaning. And suppose instead of volume and temperature, now as I have written here, PVT is there. So you have taken V and T, but you can take the another two combinations such as P and T. You can also take pressure and temperature and then fix it as constant. That means volume can be allowed to vary. So you'll have to fix the pressure and the temperature constant and then allow the volume to change. In this experiment, Helmholtz free energy will not be. It is not an energy that is going to come into picture. So instead of Helmholtz free energy, another energy known as the Gibbs free energy will become a minimum. So let me write down that. At equilibrium, remember at equilibrium is very important. If you are not going to talk at equilibrium, then there is nothing to say whether it is minimum or not. So at thermodynamic equilibrium, Gibbs free energy will be a minimum. So it is quite natural depending on what kind of experimental settings that you have in thermodynamics, the corresponding energy will gain importance. Okay, in the first choice, Helmholtz free energy will gain importance. At that time, you should not talk about Gibbs energy. That is what I mean to say. So a similar kind of principles are it is there in many areas of either science or even away from this. So in general, anything in nature, you will be able to see some kind of extremum principle. That means minimum maximum principle. And today we have seen the statement of the Hamilton's principle and the meaning. So there should not be any confusion or there should be no difficulty in reading this one, because all the technical terms that are coming into this particular statement is explained. And why there should be an integral, that's not you should not consider why integral should be there. Okay, depending on a problem, you have to decide what should be the action. So that is the difficult point here, or that is a difficult place. And Hamilton has discovered that this object means integral of T1 to T2 of that Lagrangian would be a suitable choice to act as action. Okay, if what is the action is not clear, then nothing can be done mathematically. So that is the very crucial place, and that is where the big discovery lies in. First of all, discovering what to be written for action. Okay, so that is the thing, and we will see in the next class how to write down the delta of L. Just now I said that delta of the L means the variation of the Lagrangian. So we will write down the expression for the delta of L. By writing that, what will happen is we will be able to get an equation, namely ultimately it is going to be a differential equation because the delta is there. Delta will represent a derivative, right? So therefore, if we will be getting the differential equation, that differential equation is known as Lagrange equation or Euler-Lagrange equation. So in the next class, we will see how to obtain the Euler-Lagrange equation starting from Hamilton's principle. So that is what we are going to see in the next class.